Hello, welcome back to the channel. Hope everyone's on good form. I've not done a video in a while, so I do apologise for that, but I couldn't resist filming this one. If you take a look behind me, we've got an awesome valley, and in front of me we've got a monster house. This is a beautiful old stone-built house in Lancashire. One of the ones that a lot of people will say cannot be heated by heat pumps. So we stood up to the challenge, we've done it, we've delivered it. A few challenges on this one. One of them is the heat loss is obviously pretty high with it being stone built. I'll just show you the scale of it. If you see, we've got this huge room at this end, and then there's like the upper house there almost. So it is a bit of a monster, but it's beautiful, the area itself. Now, it was heated with a huge oil boiler in the basement, and then they had a massive oil tank, which is where we've installed the heat pumps. So we've got two heat pumps that are, I'm trying to think exactly what the heat loss is. Heat loss is 26 kilowatts. The heat pumps themselves can do 28 kilowatts, actually a touch more than that, and that's with defrost as well. They can deliver that like true heat output. We've cascaded them together here. So what we did was remove the oil tank from this area. Obviously we've had to remove the fencing for correct airflow. Pipe works on the back there, running down into the basement. So yeah, big horrible oil tank has come out. This is the corner of the house that no one sits at essentially. So we've got the basement plant room behind it, bit of a utility area, so sound isn't an issue. And then from an aesthetics point of view, there was a big horrible green tank there. Now there's two nice new heat pumps. So I'll show you inside because the plant room's a bit different than normal. We've had to use a heat exchanger, and there's challenges with heat exchangers and heat pumps. You've got to get the design right so we're not getting any loss of heat along the way as we exchange heat, and I'll tell you how we've done that. So I'll just nip downstairs quickly and show you that. So I'm now down in the plant room, and I'll show you the what sometimes are showstoppers for heat pumps. First one being no water main, so our spring-fed water treatment plan there. The next one was the old hot water distribution system pipe work, and the types of showers we've got in the house didn't lend themselves to pressurised hot water, and the client didn't want to risk pressurising the hot water side, so that cylinder has been piped up, open vented, and what we mean by that is the current tank that's in the loft space, the feed and expansion tank, is feeding that. It's not fed by a water main, so it's low pressure. Again, if you take a look at the existing heating pipe work, steel, okay, again, client didn't want to risk pressurising that, so what we did is we hydraulically separated it. True hydraulic separation. We're not talking buffer tanks here, we're talking heat exchangers. So what we want to do with the heat pump is not lose any temperature along the way. So if we're flowing at 40 degrees, for instance, from the heat pump, we want to deliver that to the radiators. We don't want to lose any temperature along the way. And as you exchange heat from one heat exchanger to another, there's got to be a bit of a drop to a certain extent. So what we did is we designed a specific heat exchanger for this job. It's designed to take the heat of both of the heat pumps and deliver it with only a 1 degree drop across it. So if we're flowing in at 40, we should be getting 39 out, and we're actually getting slightly closer than that. We designed it in such a way that we've got a very low pressure drop across it, so our pumping pressures didn't have to be too high, and it's actually working really well. I'll just show you it. It's not got its insulation jacket on at the minute, but that is the heat exchanger. Now it's huge. A lot of engineers that are used to installing heat exchangers on high temperature applications might think, crikey, 26 kilowatts, that's massive, and it is, but we've done it for those reasons, okay? So that's that. We have got a 500 litre hot water tank because of the size of the house and the amount of occupants that can be in here. We have got the heat exchanger. We've got a big Belimo valve there. That is the distribution pump. That thing in the corner is a volumizer, not a buffer tank. So we've piped direct. So we've piped direct to that Belimo valve there. and then straight into the heat exchanger, yeah? And then back to the heat pumps via the volumizer. So we've no distortion there, okay? So it's a cascade, but we've combined the pipe work so we don't get distortion, and we've piped straight to the heat exchanger back via the volumizer to the heat pumps. And then the distribution side is off that honking big pump there. I was just showing the client, and I might actually put the Testo Smart Probes on. We went to the index circuit, our furthest circuit, and I'll show you the room that's in a second, because it's a big room and we've got some big radiators in there. And we were flowing, because it's quite mild today here, this morning I did have to put the heater on my car. It was about, I think it was about 8 degrees this morning, so there was a requirement for heat, but the heat pumps were only flowing at 33 degrees, I think, when I got here, 32, 33. And on our index circuit, our furthest radiator, we had lost from the heat pump to the flow of that radiator, it was 31, so we'd lost only 2 degrees from heat pump into the plant room, across a heat exchanger, all the way to the far end of the house. We'd only lost that 2 degrees, so I'm really pleased with that. It's going to be a good one, this one. We've changed every radiator in the house. We put some honking big K3 radiators in, designed at a 45 degree flow temp. We couldn't get it any lower because of that big room at the end. We can run lower if we exclude that far room, but obviously we've got to base it on our worst performing room. But yeah, that's it. I'll take you down to that big room and show you, because it's nice, and it's a tough one to heat. Okay, so I'm now in the room that contains our index circuits. This is our hardest to heat room. Now this is, I describe it as a seasonal room, so it'll be used when the family want to use it, essentially, because it's a big one. It's a beautiful room. If you have a look, it's got 3 outside walls with quite a lot of glazing, and it's incredibly high. Okay, so what we've had to do is install a lot of K3, and there's another one down here, radiators, and there is one there. But that rad down there is our index circuit. So that's it does just so happen to be the furthest away radiator from the plant room, and with the highest pressure loss. And I put the smart probes on that in there and that in there. We're only losing that 2 degrees, so that's cool. What else was I going to say about this? Yes, so like I say, seasonal room, so that's why there is TRVs on this room. So this will be isolated from the rest of the house and run at a much lower temperature for most of the year, and then when they want to use it, they can turn it up, use it, light the wood burner if they want, jobs are good, and which is fine. Rest of the system will be open loop. Well, it is open loop, pure weather compensated. Excuse me. And yeah, so it makes for a really efficient system. I'm expecting a seasonal efficiency of around 3.8 on the conservative side, but if we really tweak it, I think it will be 4. I'm gonna put my neck out there and say it'll be about 4. So on the annual service next year, we'll check it out and see what it is. Any questions about this job, put them down below. Cheers. I was just editing the video and I thought I hadn't been quite clear enough about the layout of pipe and the reason why we'd done what we'd done. So I've drawn it out on this board and I'll talk you through it. Basically, most modern heat pumps need to work on a pressurized system, so they'll need a minimum pressure to actually function. So you'll typically always pressurize a system. So what that means is if you've got a header tank that feeds your central heating system, we'd remove that, we'd fit an expansion tank, we'd fit a filling loop and make the system pressurized, and we'd run it at between 1 and 1.5 bar of pressure. Due to the age of that property and the standard of pipe work in there, there was, because it's old steel pipe work that's been in there for decades, the customer didn't want to risk us pressurising it. Totally understandable. So the solution we came up with was hydraulic separation by fitting a heat exchanger. So essentially we've got the heat pump unit, we've got the heat exchanger here, hot water tank, volumizer, radiator circuit, and then the header tanks in the loft. So if you imagine we've got the heat pump with its pump in, it'll drive the water through to the diverter valve. Now, depending if it's doing heating or hot water, if it's doing hot water, it'll run through the cylinder coil, back to the heat pump via the filter, etc., back to the heat pump, and that's that. Now, all this pipe work and this heat exchanger and that coil is pressurized. It's got an expansion tank and a filling loop. That will be run between 1 and 1.5 bar. Now, this side of the system, the existing radiator system, we didn't want to pressurize. So this heat exchanger has been installed, and it's a plate-to-plate heat exchanger. It's a gasketed heat exchanger, so we put layers of plates with gaskets in between, and every alternate plate will have one side of the system water in, and the other alternate plate will have the pressurized side of the system in. So ultimately, you imagine the water's going up one side, skipping a plate and coming down the next one. So we can exchange the heat from plate to plate. So that goes in, all that side's pressurized. This side then can be left with the header tank in the loft to keep it pressurized just on the head of water from the tank in the loft. So it'll be much lower pressure, less than half a bar with the height of that building. Okay, the second side of it was the hot water system. The customer didn't want that pressurizing either. All the bathrooms that's in that property have old pipework and old valves that don't lend themselves to being on pressurized hot water systems. So again, if you install a new system with a pressurized cylinder, that'll typically be fed via a 3.5 bar pressure reducing valve, and then obviously it'll heat up and have a little bit more pressure than that in. So what we did was we left the existing feed and expansion tank in the loft and fed the new cylinder with the oversized coil in to be fed from that. Okay, so if you imagine we've got an old way of doing things here and the new way of doing things here linked via heat exchangers. So I hope that makes sense. If there's any questions on that, put it in the comments below. I just wanted to address a comment I made right at the start of the video where I said a lot of people will say that you can't heat properties like that with heat pumps, and I want to show you how and why we can do it using this example. So if you imagine we have two houses exactly the same size, let's just say for easy reckoning that both properties, so I'm drawing houses here, I know my artwork's not amazing, but imagine they are both 100 meters squared floor area. Okay, so they're both exactly the same size. Now imagine that that house was built in 1970, okay, with single glazed windows, no cavity wall insulation, no loft insulation, so quite a drafty house. Now imagine this one was built in 2025, fully well insulated, double glazing, built to current building regulations. So really tight, really low heat loss. So same physical size, different ages, different build constructions. So if we were to do a heat loss calculation on these, we would obviously have a higher heat loss in that house. Now I'm just using these numbers as examples, so you don't read into them any further than that. Let's say that house had a 15 kilowatt heat loss. Okay, and this one had a 3.5 kilowatt heat loss. So the old property that's draftier will have a higher heat loss. People will assume that that cannot be heated with a heat pump. If I install a heat pump that has a 15 kilowatt output on it with radiators, they're obviously going to be quite large, designed at 45 degrees Celsius, that house will get warm. 15 kilowatt heat loss, 15 kilowatts going in at a design temperature of 45. With most modern heat pumps, you will be getting a seasonal efficiency of 3.8, okay, 380% efficient, 1970s house. This new house, if I was to install a 3.5 kilowatt heat pump on it, with radiators, obviously a lot smaller than those, designed at 45 degrees Celsius, I will get an efficiency of 3.8-ish, okay? That'll be warm, that'll be warm, that'll have a seasonal efficiency of 3.8, as will that. Now, The only difference is the capital expenditure to do that one will be higher than that one. But both will be warm, both will be efficient, both will work. So hence why the property you've just seen that is really old, solid stone, it's had a little bit of insulation in the loft and it's had windows upgraded. Because we've designed that system at a 45-degree flow temperature at -3, we will get a reasonable efficiency, like I said, at least 3.6, but heading upwards towards 4 if everything goes to plan. They'll have an efficient system that will cost them slightly less to run than oil, and they'll be warm. Okay, so any questions on that, fire them down below.